All right, thank you. As mentioned, my name is Todd Fauché. I'm the FCC Licensing Technology Manager for Shell Catalyst and Technologies. And today my topic of discussion is on Shell's proprietary FCC Kinetic model called SHARC. SHARC was developed by Shell over decades of research with internal research programs from pilot plant studies to FCC unit operations. It's used extensively throughout the Shell system wherever we have an FCC. It's also licensed outside of Shell to third-party customers. SHARC can be used for day-to-day monitoring activities, economic evaluations by unit engineers, future feed considerations by the economics and scheduling team, and also can be integrated into the online optimizer through the advanced process control team. We'll discuss these individually throughout the presentation. So this is a cautionary note put together by the Shell legal team. It's quite big and ominous looking. I'm not going to read everything word by word, but I will summarize it for you. And basically what it says is that you shouldn't make any economic or financial decisions based solely on today's presentation. So before I get into talking specifically about SHARC, I'd like to take a minute to talk about all the different FCC portfolio options we have within Shell Catalyst and Technologies. Of course, you see SHARC, our Kinetic model, as one of those FCC programs in our portfolio. We also have FCC licensed hardware that we offer on the reactor, regenerator, and flue gas section, including feed nozzles, riser internals, cyclones on both the reactor and the regenerator side. We also have reactor stripping technology. We have regenerator air grid technology. We also have spent cat inlet distributor technology. And then we have catalyst circulation enhancement technology. And then on the flue gas side, we have third stage and fourth stage separator technology. We also offer a range of technical support options for third-party customers, including diagnosis and troubleshooting through technical support agreements. We offer different training opportunities. We have an FCC process basics course called our M145 cat cracking course that we offer. We also offer an operations safety course called STORM. We have a full complement of R&D facilities and an R&D team that works and we do pilot plant testing of feeds and catalyst, as well as the feed nozzle testing and design and other materials testing as well. And then we have CFD modeling capabilities. So this is an outline of today's agenda. So I'll talk a little bit about what SHARC is, the basis for SHARC, its fundamental concepts, and who would use SHARC. We'll talk about the development history of SHARC dating back all the way to the 1940s and the initial kinetics research. We'll talk about how SHARC works, the different parts and pieces of SHARC, the SHARC model that take the inputs and produce the outputs. We'll talk a little bit about the uses for SHARC from unit engineer doing day-to-day monitoring to projects evaluations to spot opportunity evaluations to online optimization uses. Talk a little bit about benefits and features, including the different interfaces that can be utilized within SHARC, the different operational modes. Talk about different help features within SHARC, and of course the different properties, feed properties, product property generation capabilities. Then I'll have a summary slide, and then we'll wrap up with a Q&A session. So what is SHARC? Well, let's start with the acronym itself. So SHARC stands for Shell Advanced Rigorous Cat Cracking Model. Okay, so it's a model developed by Shell based on decades of R&D research and includes over 50,000 different test runs from pilot plants and FCC unit operations. And all of that was done to generate a set of proprietary kinetic correlations as well as feed characterization correlations. This put into the model that has different other components to do heat and mass balance closures, produces what is the SHARC model. That kind of describes SHARC as the program, but SHARC as it's used by the individual really comes down to a base case. So a SHARC base case, what is that? A base case is a representation of your specific FCC model within SHARC. So it encompasses what kind of hardware you have, what kind of catalyst you're using, and it also encompasses all the different operating conditions, feed rates, and different types of feed that you utilize within your unit. So on the hardware side and the catalyst side, that information is input directly into the SHARC model itself through different hardware components that are available within SHARC to characterize as well as catalyst. The different operating conditions and feed rates and feed properties are taken through different test runs, which are basically feed and property samples that are done in coincident with taking the unit data. So each one of these test runs, and usually for a base case, you would take somewhere in the range of 5 to 10 different test runs that would span the different kinds of unit operations that you would run, and also the different types of feed and feed rates that you would run. All of that information comprised into a test run is put into a program that we call Data Pump. And Data Pump is basically a very advanced Excel spreadsheet that takes each one of the test runs that you generate and does a check against heat and mass balance, and then it normalizes this data, basically meaning it gets it ready for import into SHARC and production of the base case itself. So now you have a base case. What do you do with that? So base case is used as your baseline, and then you generate weekly or bi-weekly test run data to compare against that base case to check unit performance. Beyond doing unit monitoring, SHARC can be utilized to generate base plus delta vectors to be used in the LP model by the economics and scheduling team. And it also can be used to run the online optimizer for the FCC. Of course, this, I've already mentioned, this is used within Shell, but it's also available for license outside of Shell. The history of SHARC. So it dates back all the way to the beginnings of FCC in the 1940s and 50s, when Shell started to initially look into FCC kinetics and began an R&D program. In the 1960s, Shell was able to develop the first FCC kinetic model. It's the precursor to SHARC. It was based mainly on gas oil feeds and silica aluminum catalyst. It was very accurate, but it was very slow and cumbersome due to the complexity of the model. In the 1970s, Shell was able to expand the FCC kinetic model to cover resid feeds. It also was able to generate better kinetics through selectivities, kinetic selectivities or selectivity ratios. And then it also implemented a feed characterization property, which was able to greatly simplify the ability to characterize the feed. It also produced a faster and easier to run model. In the 1980s, the model was further improved and made faster, such that it was first implemented within the first Shell Online Optimizer. In the 1990s, another R&D program was developed to get even more data for improved kinetics. And this was really the first release of SHARC. And so ever since that first release, Shell has been updating and improving SHARC and continues to do so today. In fact, the next release of SHARC, which is version 3.5, will be available sometime in 2021. So how does SHARC work? Well, SHARC is made up of a bunch of different submodels, correlations, and equations that takes the inputs from the user. These inputs can be are around the individual feeds that you want to use, the recycles, any catalyst and additive data that you have if it's different from the base case, any different kind of operating conditions that you want to input into the model. And then it also encompasses any unit constraints that the model has. So this would be around, capacities, limitations on such things as the wet gas compressor or the main air blower, or maybe catalyst circulation rates. So all of these inputs are put into the model, and then the different submodels, if you will, generate the outputs, which basically the yields, the product properties, and the resultant operations. So the different submodels include the kinetics or the yield model, of course. This basically generates the yields and the different selectivities. There's also a stripper model, which models the efficiency of the stripper, the hydrogen and coke. There's a heat and carbon balance component or model that determines the cat circulation rate as well as the resultant operating conditions for both the reactor and regenerator, like the regenerator temperature itself. There's a regenerator model that predicts the fluid gas composition as well as the air rate needed to burn the coke. Within the regenerator model, there's a further submodel for the CO boiler if you're in partial burn. This takes the CO composition in the flue gas and can predict how much fuel gas you need to combust the CO, as well as predict the amount of steam you generate and the resultant flue gas composition and operating conditions out of the CO boiler. There's a product property model. So this would basically predict the different liquid properties for gasoline and heavier, and typical properties that it predicts are density, viscosity, sulfur content. And for gasoline specifically, it will predict octanes and piona. And then for LCO, it'll predict the cetane. This can be done at standard cut points or at user-defined cut points, giving the model further flexibility. There's also a catalyst deactivation model. So the catalyst deactivation model gives a better predictor of ECAT properties such as activity based on feed composition inputs as well as regenerator temperatures and CRC. So the logistics of the model, how does it work? Well, so there's an interface where the inputs are put in and outputs are received. So there's three different types of interfaces that we have for SHARC. There's your typical normal GUI interface that we have, which is more tabular in nature, and I'll show a picture of this interface later on. It's good for entering information on the different components and executing the model and seeing how it affects the model. But then there's also a flow sheet simulator, which is more along the lines of what a DCS screen or a Pro2 simulation would look like. So this has the capability of changing some inputs, executing the model, and seeing the impacts over the full range of the model, not just the screen that you would be looking at on the normal interface. The final interface is an Excel-based interface, and this is basically uses the data pump feature that I was discussing before. You can run the full version of SHARC within the Excel model. So as I mentioned, you have inputs. Those inputs go into the SHARC model, and the SHARC model, as I've described before, is a bunch of different submodels, which has a bunch of correlations and equations in those. Those equations are sent to an equation solver that solves these equations simultaneously. And then it spits back out results and sends it back to whatever interface that you happen to be using. This describes how the standalone model works. Of course, I've also mentioned that the SHARC model works with the optimizer. So the optimizer would control SHARC directly, put in inputs, receive outputs, and be able to work the optimizer directly with SHARC. Also, there's outputs from SHARC that can be generated to basically give the vectors that can be used in the LP model itself. So what are some of the uses for SHARC? So SHARC has many different uses, going from day-to-day unit monitoring type uses all the way through specific opportunities, evaluations. Looking at the unit monitoring side of things, SHARC is used to basically evaluate the performance of the unit against the base case in order to help the unit engineer do early detection on any issues that there might be on hardware or catalyst. These kind of issues on hardware or catalyst are hard to detect by just looking at trend lines or trends, such that you might be able to do, say, with fluidization issues or with slide valve DP issues. And the reason for this is the fact that the product properties and operating conditions are constantly changing. So you really need a base case that is able to predict these changing conditions and compare how your test run, your specific test run is performing, or how it compares to that base case. You can also use SHARC to evaluate new technology, or new catalyst. This basically can be used to provide the economic evaluation or the case for change, if you will, for going to the new technology or catalyst. It can be used for economic evaluations, such as evaluation of purchased feeds, or whether or not you want to use additives in your FCC unit. This, combined with the catalyst deactivation model that I mentioned previously, helps to accurately predict the impacts of different feeds or different regenerator conditions on the ECAT itself. SHARC can be used for predicting or seeing what alternate operations will do in predicting the yield and the resultant regenerator operating conditions from that. I've already mentioned that SHARC can be integrated into other refinery tools, such as the LP model and the optimizer. One thing that I haven't mentioned yet is SHARC is a good tool for training, especially for new engineers and for new operators, especially when using the flow sheet interface. You can use that flow sheet interface, change some of the inputs, hit execute, and see exactly how the model will react. So it's a very good training tool in that regard. So as far as unit monitoring or troubleshooting is concerned, unit monitoring is one of the key activities for the unit engineer. As I mentioned, it's used for early detection of any issues so that corrective action can be done as promptly as possible, helping the FCC unit and the refinery in general save money and retain margin. This starts with getting test runs on a weekly or bi-weekly basis and comparing these test run inputs against the SHARC base case. So I've already mentioned that you really need a SHARC model or FCC Kinetic model comparison of test run information against a base case to really predict if there's an issue on hardware or catalyst or not. It's not as simple as just looking at trends. I mentioned that was because of the constantly changing feed properties and operating conditions. So having a good kinetic model or base case is essential for this activity. When the unit engineer does his weekly or bi-weekly test run and compares it against the base case, if there's complete alignment or the results match fairly good, then everything's running as it should. Once there starts to be a deviation or a gap between the test run information and the base case information, then the unit engineer knows that something's not quite right and they need to do some further investigation. So at that point, he really doesn't know what's going on. He just knows that something's going on. So within SHARC, there's different analysis and performance normalization and performance analysis tools using different selectivities and hardware efficiencies that help to narrow down what the issue might be. So once the unit engineer understands the issue better and is able to narrow it down, he's able to work with the operations and other unit teams to develop a path forward. If it's on the catalyst side, it could be as simple as increasing catalyst addition rate, or it could be as complex as going through a reformulation evaluation for the catalyst. On the hardware side of things, if you recognize an issue on the hardware, then that's when you are able to identify that issue and bring it to the attention of the unit management team and get it on the turnaround planning. So another thing that you can do with SHARC beyond just unit monitoring is you can determine where SHARC is operating now versus where it could operate at its full potential. And this is an evaluation that can be done to make a case for change for either evaluating new hardware or new catalyst. So SHARC has within it a metric called max net conversion, so that evaluates the FCC unit if it were operating at its full potential. That can be compared against the actual net conversion to see how much room to improve that the unit might have. And then, of course, using SHARC, you can tell whether a new base case is needed or not. So beyond just having a gap, like you might see within a potential hardware catalyst issue, when you have a base case that needs to be updated, you have different responses that will happen between the base case, the way the base case responds, and the way the test run information responds. Another use for SHARC is for evaluating purchase feed opportunities. So SHARC has quite a bit of flexibility built into it. It has the ability to analyze up to 6 different feeds, ranging anywhere from VGO to resid to DAO, and it can be hydrotreated or unhydrotreated feeds. It also can evaluate up to 3 different recycle streams, LCO, HCO, and slurry oil. So with this functionality and flexibility, you can have your existing feeds defined, and you can then define a new feed in one of the unused feed slots, if you will. Using this, you can evaluate the economics and the effect on the units based on yields and operating conditions, as well as the catalyst effects. You know, this within the model, I've already talked about the catalyst deactivation model. You can utilize that to more accurately predict these feed opportunities, how that will affect the ECAT. So there's two different modes of operation within SHARC. There's a simulation mode and there's an optimization mode. So within the simulation mode, if you know exactly what kind of feed you want to run, what the rate is, and what the operating conditions are that you want to run, you can run that and see what the impact is on the yields and the resultant operating conditions. It will use within the simulation mode, it will use the unit constraints to determine whether the operation that you've chosen falls within constraints, or if it falls outside of the constraints, it'll give you an error message to tell you what constraint you violated. But there's also another mode of operation called the optimization mode, and this is quite handy within SHARC. So within the optimization mode, you get to choose your objective function that you want to maximize. And there's a choice of 6 of them. And I'll go into more detail later on as far as optimization mode. But basically what you're doing is you're allowing the model to change you know, the inputs that you have. So you can, and it runs within the model, within the unit constraints. So it will not violate the unit constraints. So it finds the maximum objective function solution within those unit constraints. So within the optimization mode, you have several different choices. You can choose to vary the feed or not vary the feed. You can basically you know, look at the feed and see what the outcome is, and do an economic evaluation based on the outputs and determine whether that feed is something you want to pursue. Another evaluation that you can do is an evaluation on different operating conditions, alternative operating conditions. So some similarities to the opportunity feed evaluation. You have the same number of feeds that you can you have to play with. So you have 6 different feeds, you know, ranging from VGO to resid to DAO, hydrotreated, unhydrotreated. You have the same recycles that you can play with. You have the same different modes of operation. So you can do simulation mode again and see if you know exactly the operation that you want to simulate, and get and directly get what the changes are to yields and resultant operating conditions. Or you can use the optimization mode to let the model vary the inputs and operate within the unit constraints to maximize the objective function that you've chosen. Already talked a couple of times about the catalyst deactivation model, but I'll make another plug here. If one of the operation modes that you're considering changing is, say, regenerator mode, this catalyst deactivation model is very good in taking changes in regenerator temperature, changes in CRC, and accurately predicting the effect that it will have on the ECAT properties. So some of the SHARC features and benefits, some of which I've already mentioned a couple of different times. So I've already mentioned that SHARC can be used for studies and of course unit monitoring. It's can be fully integrated into other refinery tools. One of the things that I haven't mentioned yet is that SHARC is not just for Shell FCCs. SHARC can be tuned for any FCC. Has many different useful and flexible features such as choice of units of measure, choice of standard or user-defined cut points. I've already mentioned the many selections or the many individual feed streams that you can set up. You have different recycles that you have to choose from. There's also a quench selection. You can put in posterizer quench if you want to. SHARC has the ability to export files from one model and then take those exported files and re-import them into another model. So this has to do with, say, different feeds, economics, test runs, and the like, and that basically helps so that you don't have to manually input the information in every single time. You can export from one model and import into another model. SHARC has the ability to generate different reports. You can generate a report into Excel, a data dump, if you will. You can also generate an input file for Pro2 so that you can take that input file and it'll directly give you the reactor effluent, and you can use that to run a Pro2 simulation. I've already mentioned the different modes of operation, whether that be simulation or optimization modes, and some of the different features and advantages of simulation mode and optimization mode. So just to recast, simulation mode is when you have a specific set of operations you want to check out. Optimization mode is when you want the model to choose the inputs and find a solution based on maximizing the objective function that you have chosen and stay within the constraints. Another nice feature of SHARC is that you run the model, you can run it and compare a single test run against the base case, or you can run a bunch of different test runs at a single time, up to 15 different cases, and compare those. Mentioned some of the built-in correlations and estimating features for feed and product properties. There's also the catalyst deactivation model that I've mentioned, and then of course the different user interfaces that I've discussed before, as far as being able to utilize either the normal interface or the flowsheet interface or the Excel interface. And then, of course, the improved profitability, which has been demonstrated within the Shell system for a properly tuned base case model. So for a properly tuned base case model, Shell has been able to demonstrate that you receive a benefit of anywhere from 10 to 50 cents per barrel. So talk a little bit more in detail about the feed property generator. So the feed property generator is extremely important to get good feed characterization. Basically, you're able to generate from a select amount of feed data that you have, you're able to generate more feed information, more feed properties that that allow you to fully characterize the feed, because the more information you have about the feed, the better and more accurate prediction you're going to have. So Shell has some minimum inputs as far as feed is concerned. You have to have the distillation, density of some sort. You have to have feed coke that can come in the form of CCR, MCR, or even an NBC. You have to have sulfur and nitrogen content in the feed, different metals, and a viscosity. So that's kind of the minimum information that's needed, and from that, SHARC can generate much more information, including but not limited to, so the UOPK value, molecular weight, aromatics, and so forth. This feed property generator can be applied to each of the 6 different feeds individually. So it's applied to the different feeds one at a time. It also can be applied to the different types of feeds that I mentioned before. So it will generate different properties based on the type of feed that you have, whether that be a VGO feed, resid feed, or a DAO feed, hydrotreated or unhydrotreated. These properties, once they're generated and put into the model, you have the ability to export those properties to a feed input file, and then import those feed properties to another SHARC model. So that's very beneficial. Again, saving you time having to manually input stuff. So we've talked a little bit about the different modes of operation. I mentioned simulation mode and optimization mode. So again, simulation mode is it's to see the impacts of a specific set of changes you want to make within the model, whether those impacts are on feed or operating conditions or whatever, and see how those impact the yields and the resultant operating conditions. You have up to 6 different feeds and 3 different recycles to apply these changes to. You have a bunch of different choices on how you want to reconcile the heat balance. So for instance, you could choose to specify the coke make and the air rate, or if you weren't sure about one of those, you could choose to specify the preheat temperature, or this and the CO content or the O2 content, depending on what kind of regeneration mode you're in. You could also look at constraints. It uses the constraints, but it doesn't force the solution to fall within the constraints. So, but it will give you a message if you do violate the constraints. If you do happen to try and solve or find a solution that's not solvable, it's an infeasible solution, the model will give you an error message on that too, but it'll return to the last feasible solution. So you're not stuck with an infeasible solution. Again, you can use simulation mode to compare a single test run against the base case, or you can use it to do multiple cases at a time, run them simultaneously and compare them, which is sometimes very beneficial. Optimization mode, of course, it has some similarities to simulation mode in the sense that you have the choice of all the different feedstocks that you can use, as well as the different recycles. But the optimization mode itself, the essence of it is you want to choose an objective function, and there's different objective functions for which you can choose. There's 6 different ones you can choose from, ranging from maximizing profits to maximizing conversion, maximizing gasoline, maximizing LPG, maximizing LCO, and maximizing octane. So you choose one of those objective functions. Then you can also, unlike simulation mode, you can choose to vary the different feeds if you want to, as well as other input conditions to maximize the objective function. So, so optimization mode has some key benefits to it for evaluation of different opportunities. Whether that be an economic opportunity or a yield type of opportunity, to see how the unit operates within the constraints, but see how the yields fall out, as well as the resultant operating conditions. Okay, just to summarize here, talked about SHARC being it's what it is. It's Shell's proprietary FCC kinetic model. It can be used to tune any model to fit any FCC model, not just a Shell model. It's comprised of a bunch of different submodels and correlations and equations, such as a stripper, regenerator model, catalyst deactivation model, CO boiler model, just to name a few. It's based on a lot of research that dates all the way back to the 1940s and the original kinetics R&D work that Shell did, but it's been progressed along the way. It's consistently updated through an ongoing R&D program that we have here at Shell. And this really helps to drive the accuracy and the confidence in the results that the SHARC model has. SHARC as a base case can be used for basically setting up a base case, can be used for unit monitoring and a lot of different things, but setting up the base case, getting the test runs to do that over a range of different operating conditions and feed rates and feed conditions gives the base case model a robustness and a flexibility and an accuracy level that really sets SHARC apart. Has lots of built-in features. Some of the ones that I've mentioned previously are the different interfaces that it has, the different property generators, feed property, product property, generation capability, the ability to simulate a direct result or optimize within a chosen objective function to find a solution. The different import and export capabilities as well as report generation capabilities so that you can use the output directly into a Pro2 simulation. The ease of use of SHARC, so the different interfaces that it has, especially the graphic interface or the flow sheet interface can be used for SHARC training for new engineers. It integrates into the other refinery tools, such as the LP model and the online optimizer. And the uses itself, already mentioned the unit monitoring, but it can be used for economic evaluations for feeds and catalyst and different project evaluations, basically providing you with the case for change. Mentioned that SHARC has a demonstrated profitability for a properly tuned base case of anywhere from 10 to 50 cents a barrel. And then, of course, the last piece is that SHARC is a Shell program, but we license it outside of Shell. So that's all I have. Thank you for your time. If there's any questions.
Thank you so much, Todd. And let me just share the Q&A screen. There are several questions for you. The first one is from Alan Kramer. Can you please expand on the capabilities of SHARC to perform catalyst selection predictions? What inputs or data are required to do this? How accurate are the results?
Yeah, so we basically do this a lot within the Shell system. What we'll do is we'll take the different inputs that we get from the catalyst vendors regarding the catalyst type and the different catalyst properties, the surface area, ZDM ratios, all those things. We'll put those into the system, and we'll do that along with some feed. So we'll get a feed sample that from the site that's considering a catalyst evaluation, and then we'll evaluate the catalyst performance. So we do that in our pilot plant, and then we test. We input those results into SHARC, and we normalize them. And so those results are compared and contrasted against the results that the catalyst vendor may produce, and it generally sparks conversations about you know, if there's different directions that that our predictions might be showing as far as yields or whatever versus what the catalyst vendor may show.
Okay, our next question is from Brian John. What are the major advantages or disadvantages of SHARC versus other kinetic models such as prophymatics?
Yeah, so I think one of the major advantages is the fact that we take a base case, or it's developed over a full range of feed rates and feed properties, as well as unit operating conditions. So it has a lot of accuracy and flexibility within that range. So you can move within those different operating and feed parameters and have a lot of accuracy for the base case. And it's like I mentioned before, it's the base case is set up on somewhere between, say, 5 and 10 different test runs. So there's a lot of rangeability built into the base case model.
Okay, Alan Kramer asks, how does the model handle feed blending? Does the model create a combined feed from the individual feeds? How accurate is it in handling dissimilar feeds? For example, adding tight oil or adding a slipstream of resid in a VGO unit?
Yeah, so yeah, you kind of hit the nail on the head on the first one as far as feed blending is concerned. So you've got 6 different feeds to choose from. So we typically like to get from the site, we like to get the individual feed properties so that we can do our own blending within SHARC. Sometimes that's possible, sometimes it's not. But SHARC does a really good job of being able to blend different feeds and come up with a good and accurate result. As far as VGO and resid, we've been able to blend those in our shell FCC units quite predictably. Light tight oil, that's a good question. I don't know that we've ever tried to directly blend LTO into SHARC. I might have to look into that one and see if I can get the answer on that one.
Okay, from George Hoekstra, does the model calculate sulfur type distribution in FCC gasoline? And what kind of model is used to calculate octane in the gasoline?
So yes, it does calculate a sulfur distribution within the different products. Doesn't necessarily go into specific sulfur speciations, if that's what the question is, but it does calculate a sulfur distribution between the different products. And as far as the kind of model to calculate the octane in the gasoline, I'm not sure I completely understand the question, but it's basically a Shell proprietary property model that we've developed to calculate the octane, if that answers your question.
All right, from Todd Miller, is the license based on a user or on a specific unit? i.e., can I get one license for myself and build models for multiple units, or do I need a license for each unit model, which can then be run by anyone with the software for that model only?
Yeah, we typically base a license off of the different models. So you would need to have a license for each base case, if you will, each unit. And we typically help the third party update the base case and prepare the base case. You know, we don't just give you the software and say have fun. we actually help you with generating the base cases as well. But we have had opportunities where clients were interested in multiple licenses for multiple units, and we have looked at that in the past and how to I guess let's say cost effectively do that so that it makes it cost effective for the client.
Mel Larson asks, what is the programming language that SHARC is built in? With Shell divesting of so many refineries, is Shell expanding their support services back to those facilities?
Yeah, so the base language is C++, I believe, and the second part of with Shell divesting of so many refineries, is Shell expanding their support and services back to those facilities. So yes, we're maintaining our support back to the divested facilities if those facilities are interested in continuing support. Absolutely. So we're looking, we not only support our units, but we, through technical service agreements, we are able and willing to help other third-party clients, whether that be former Shell units or units that had no previous affiliation with Shell.
Okay, Mel Larson asks, how does the model develop the reactor effluent problem, such as its contiguous?
Contiguous. So there's if you remember the slide I had before, one of the slides, there's a bunch of different submodels within the SHARC model itself. So there's and all of these models kind of feed into and out of each other. So there's a kinetic model, there's heat and mass balance models, and then there's regenerator models. All of those kind of feed together to do the heat and mass balance, cat circulation rate, but also do the kinetics and the properties as far as reactor temperature and stuff like that. Of course, some of these properties are built into the inputs. So for instance, pressures are inputs. So pressure of the regenerator, pressure of the reactor overhead are inputs. Reactor overhead temperature is likely input as well, but you'll have resultant conditions such as stripper temperature, regenerator temperature, and the like.
Okay, the last question, does the model provide speciation for products such as PANA, sulfur distribution by species, in the contiguous basis?
Yeah, so the sulfur speciation so we're developing more and more capability within SHARC. Right now, what we have is, I guess, it's more of a sulfur distribution within the different liquid products, but we are developing more capability in the ability to speciate different things, different products within the liquid properties, or different compositions within the liquid properties. It does do APONA, yes, for the gasoline. Yeah, absolutely. Just say good questions. I really appreciate everybody tuning in and listening to me. And if you have any further questions, I'm available. You can reach out to me. I'm on LinkedIn. You can reach out to me there. You can. I assume you can reach out to the RefCon, and if you have a follow-up question, then they'll send that to me as well, and I can answer that.